Hi, my name is Shaljeel and welcome to Tutorati. Right. Today, what we're going to do is we're going to talk about the magnetic effect of electric current. I will not be going into a lot of details. We'll be covering some very important basic laws, and then we'll be discussing a question paper. If I'm not wrong, there's a question paper that was shared on the group for you all to solve. If you have solved it, excellent. If you have not solved it, still we'll go through the paper so that you understand, okay, what were the answers and how to write those answers and stuff like that, right? To start off with a very basic note, we already know what magnetic effect of electric current is. I mean, you have already studied this, right? Basically, whenever electric current flows through a conductor, it has got three effects. We know this, right? These three effects would be heating, magnetic, and chemical. We do not discuss chemical effect today. Heating effect is something that you have already studied. The Joule's law, what you studied, right? Joule's law was basically when you studied the heating effect. Today, we are going to discuss about the magnetic effect of electric current. So, what is the magnetic effect of electric current? In the most simple language, if I want to talk about this, in the most easiest language, whenever electric current flows through a conductor, the conductor produces a magnetic field around it, right? And this phenomena, when by the conductor is able to produce a magnetic field around it with the flow of electric current, is called as the magnetic effect of electric current. I'm sure you already know the basics of magnetism. Magnets were first found in a place called as Magnesia, and it was in Asia Minor. It was the Chinese people who first started using this as a compass. And the Chinese people, by the way, called this stone, which was the magnetic stone first found, they used to call it as the leading stone. Leading stone. Why did they call it as the leading stone? Because we know the basic property. If you have to tie it up and freely suspend it, we know that this will always point in the north side direction. So this stone used to help them. It was leading them to a direction, right? But over a period of time, this name got corrupted, and in today's days and world, this stone is called as the lodestone, right? I'm just going to talk about very basic stuff over here right now because I need to focus on the three important laws in this chapter. And once those three laws are done, and if we still have some time to discuss of the paper, we could talk about the motor, EMI, and the generator, right? Apart from this, at any point of time, if there's any other question or any other doubt that anyone has, why does it points only towards north? No, it doesn't. It doesn't point towards north. It points towards north south because it aligns itself towards the Earth's magnetic field. The Earth is a giant magnet. We know this already, right? And this Earth is a huge magnet because clock face rule. Okay, Shranav, I'll talk about the clock face rule uh, today, but let me just first start off with the basic things, right? So as far as the Earth is concerned, we know as far as the Earth is concerned, there's this molten core. Ritvik, when you say scalar or vector, what are you talking about? What is scalar and what is vector? Right? So the core of the Earth is molten, and there's iron-based core which moves, which produces the magnetic field around the Earth. And when you place a magnet, it points north and south. So the north pole of the magnet actually points towards the geographical north, but it is the magnetic south. I'm sure you guys already know this. There's nothing new about this, right? All right. Before I even start off with discussion of the paper, we need to talk about some basic rules and laws. One of the most easiest one that we know. I'm not teaching the entire chapter today because that wouldn't be possible in an hour, right? But as I said, I'll be talking and dealing with some very basic laws, some important laws. Today's session will be primarily focused on important laws that we need to talk about, right? So first law that we need to understand is the right hand thumb rule. Again, one of the most easiest laws. I'm sure you all already know this. What does it says? So before we understand what does it says, let's try to understand where does this come from. Now, in case of a normal bar magnet, if you take up a normal bar magnet, let's say if I were to make this over here, right? Assume this is perfect. This is north and south. What happens is we get this magnetic field, right, which is shaped something along like this, right? this field is actually called as, the shape is called as the butterfly field. Why butterfly? Because it's supposed to look like a butterfly. I'll just explain how. We need to be a bit imaginative. Now if you think about this, that there's this head of the butterfly here, there's this body of the butterfly, right? And then these are the wings, right? And a butterfly field is a very desirable field because it's very strong, it's very stable, and it's everything, right? Now as far as a conductor is concerned, now you have already done this, so you know this already. If you take a straight conductor, let's say this is a straight conductor, and you pass it across from a cardboard. Let's say there's a cardboard that you pass it through and everything, and if you have to connect it to a cell or whatever, right? And if you have to dust some iron filings over here, you know what are iron filings? Iron filings are basically iron ka small powder, right? And once electric current begins to flow, right? Once electric current begins to flow, sorry, this is wrong. It goes from positive. Let this be negative and let this be positive. So current will go from here and here, right? So as I was telling you, what happens right now is as current flows, what happens? And if you have to tap this cardboard, all these iron filings arrange themselves into concentric circle. What is concentric circle? Concentric circles basically mean circles with the same center. Circles with the same center. Now understand, in case of a bar magnet that we discussed over here, we know the properties of this lines, right? We know that the direction of the field line is always from north to south. That's a very basic property. It always goes from north to south. Now the direction of field line is very important. Now whenever there's a concentric circle, how do we find the direction of field line? Because there's no north pole and there's no south pole. So what do? We use this rule called as the right hand thumb rule, right? Sanket, you're from Srinagar. Thank you, Sanket. For everyone else, I would really request you to please write down your name and if you're from Mahesh Tutorials, which branch you're from, and if you're not from Mahesh Tutorials, which school you're from. Please do that. Thank you. Right now, what does the right hand thumb rule says? Now it's a very simple rule. So just listen to this, right? We say. Let's imagine that you're holding a current carrying wire, right? This is a current carrying wire, and let's assume that the current is flowing up niche se upar, right? So as current is flowing niche se upar, what do? Is I hold this wire in so the law says, well, whether you are there, right? So hold the current carrying conductor in your right hand with your fingers curled around it. I mean, you need to curl. If you look at this, I'm curling my fingers here, right? You curl your fingers here. Once you've curled your fingers, and you need to stretch your thumb. If you, I don't know if you could see this, my thumb is stretched, see, along the length of this wire. Now if my thumb were to point in the direction of the current, is my thumb pointing in the direction of current? Yes, because I said that current is going from niche se upar, right? Then the direction of my curled fingers, if you could have a notice over here, then this direction basically gives you the direction of the field lines. What is this direction? We always start from the knuckles and you go to the tip of your fingers, right? So if you look at this from the knuckles to the tip, this direction would be what? This is anti-clockwise direction. So in this case, when we know that the current is flowing like this and I'm holding it like this, current is going like this, then the direction of field line is what? Anti-clockwise. In a similar situation, if I had a, let's say this is positive and this is negative, right? In this case, when current is going like this, then we know that the direction of field line would have been clockwise. This is called as the right hand thumb rule, right? Pretty easy enough. Two more important rules which are a part of this chapter for you. Someone asked me the clock face rule, but it is not a part of your syllabus. Who asked me? Shranav, you're from श्रावण क्या है? एक सेकंड में क्या कंफ्यूज हो रहा हूँ यहाँ. नहीं, श्रावण महाजन, right? Now, you asked me about the clock face rule. I'll explain you the clock face rule in a very simple way. For others who are not even sure what is the clock face rule is a very important rule, but then it's not in CBSE. It's a part of ICSE curriculum. I would still go ahead and tell you, if you could understand that, good. If you cannot understand that, excellent, not an issue. So clock face, in the most simplest words, right, Shana? in the most easiest language, if you want me to explain this, I'll say when the current that in a coil, let's say if we have a coil, okay, and it is connected to whatever cell and stuff. In this case, if the current is going, यहाँ पे obviously it will go from positive to negative. So in this case, the current is going what, in a clockwise direction. So when the current is in the clockwise direction, the magnetic pole, acha, this generally happens in case of solenoids. I would be discussing solenoids today. Single loop mein nahi hoga. So you know what a solenoid is? It's a loop like coil of many circular turns, right? And let's assume there's a current which is going here in the clockwise direction. यहाँ से जा रहा है, ऐसा clockwise में जा रहा है. This is हाँ. If the current is in the clockwise direction, then the pole that it creates over there is the south pole. And if it is going in the anti-clockwise direction, then the pole that is developed over there, it is north pole. अब ये poles कहाँ से आ गए? If you guys are worried about यार ये poles कहाँ से आ गए यहाँ पे, because ये आता है solenoid से. Because solenoid ka, if I were to talk about a solenoid ka, if you were to analyze the magnetic field, if this is a solenoid, forgive my diagram please, right? Sorry, positive, negative, right? If I were to connect it like this, the magnetic field lines of a solenoid are shaped like a butterfly. I mean, they are in that butterfly wala pattern. Hence, we have the we have the south pole and the north pole and stuff like that. That, in short, is clockwise rule. Again, it's a very important rule, but you don't need to know as far as your boards are concerned right now for the time being. Correct? Once that is done, we'll move on to, okay, this is how you write the rule. This is the right hand thumb rule, as I was talking about. It says, imagine that you're holding a current carrying wire, right? You held the conductor in your right hand in such a way that your thumb points in the direction of the current. Now, this is important, that your thumb should be in the direction of current. Then turn your fingers around the conductor. The direction of the fingers is the direction of the magnetic lines of forces. Now, one of the most important words in this entire rule, one of the most important would be imagine. I mean, I'm just kidding, but then because you're not going to hold an actual current carrying wire, right? I had to discuss two more rules before I switch to the paper, which is Fleming's left-hand rule and Fleming's right-hand rule. Fleming's left-hand rule is pretty easy. I'm sure you already know this. If you all don't know this, I'll just explain it to you. Give me a moment. I'll just switch the slide to Fleming's left-hand rule. That's number 55. So, okay, that takes some time to load. Excellent. What is Fleming's left-hand rule? Generally, whenever we are talking about electric motor, हम जब भी electric motor की बात कर रहे हैं, let me find a place to write this. In case of an electric motor, what happens is that there is a magnet, there's electric current, and what is a motor? I'll just briefly, a motor is a device that converts electrical energy to mechanical, right? Basically, if you look at any motor, it will try to go goal, which is basically mechanical energy, because it is moving, it is in motion, right? Now, on that very similar note, if I talk about in case of electric motor, the Fleming's left-hand rule simply says that take your thumb, forefinger, and your central finger, right, and stretch them mutually perpendicular. Mutually perpendicular, they are perpendicular to each other, right? That's what it says. And it says that if right, the forefinger points in the direction of magnetic field, right, and the central finger points in the direction of electric current, then the thumb shows the direction of the force acting. The thumb shows the direction of force acting. I'll repeat. If the forefinger shows the magnetic field, right, central finger shows electric current, then the thumb points in the direction of the force or motion, because motion cannot happen without force, right? So that is one important thing to remember. Now, one very important thing that we need to understand is a lot of students get confused between the forefinger and the central finger. ये दोनों fingers का जो है they mix it up. Forefinger और central finger का लोग यहाँ पे mix कर देते हैं. Very easy way to remember. I mean, force F, magnetic field का uh, the symbol is B, and electric current ka is I. So you could remember it as FBI. If you're confused because we are using only the symbols of each thing, then you could also call it as father, mother, child. Right? Father F, force, mother M, magnetic field, child C, current. That's one of the easiest ways to remember this, right? ये तीनों अच्छा. If you have understood the left hand, the right hand becomes even more easier, right? So left hand ka what's the basic difference between Fleming's left hand and right hand? I'll just come to it, Amay, once I've explained both of them. Left, Amay, have you understood what is the left hand? The left hand says that if you know the forefinger ka, if you know the magnetic field ka direction, and if you know the electric current ka direction, then you can find the direction of force. The right hand rule says that if you know the direction of the force acting, right, and if you know the direction of magnetic field, then you can find the direction of induced current. What is induced current? Produced current. So basically यहाँ पे current है, यहाँ पे induced current है. ये एक difference हो गया. The second difference is that यहाँ पे in case of left hand rule, you need to know magnetic field का direction and electric current का direction. Only if you know ये दोनों direction, that you can find the direction of the force. In case of the right hand rule, you need to know the direction of the force and you need to know the direction of magnetic field. It's only then that you'll be able to find the direction of the electric current or the induced current or the produced current. Why is it called as the induced current or the produced current? Is because sorry, so I'll just talk about EMI. So we need to discuss EMI, which is electromagnetic induction. If you don't know, I'll write it down. Electromagnetic induction. Let us just try to understand what does it even mean. The word electro comes from the word electricity, right? The word magnetic comes from the word magnetism. And the word induction basically means production. So what are we saying over here? Understand, what is EMI? EMI simply means production of electricity due to magnetism. मतलब मैग्नेटिज्म की वजह से जब इलेक्ट्रिसिटी प्रोड्यूस होता है, हम उस चीज को बोलते हैं इलेक्ट्रोमैग्नेटिक इंडक्शन, राइट? और यहाँ पे द राइट हैंड थंब रूल बेसिकली शोज यू द डायरेक्शन ऑफ द इंड्यूस्ड करंट. तुम्हारे पास करंट था नहीं, वो करंट प्रोड्यूस किया गया था. I hope that sorts it out. Amay, if you could answer, that would be wonderful. So Amay is typing. Amay, yes, thanks. You're most welcome. Amay, which center are you from, Amay? Right. All right. Now that these were the three basic rules that we had to understand, what we'll do is we'll discuss a paper right now. Just hold on for me. Amay from, oh, Amay. Okay, Amay, I remember who you are. Take care. I'll just take the paper so that we could discuss that right now. These papers are for your help. If you were to solve them, it really helps you out, right? All right. Anyway, without much further ado, let's start off with the paper. It was a 30-mark paper, 1 hour, 30 minutes. It would just gone through. Vishal, thank you so much. I appreciate that. Right. So it should not have taken you 1 hour 30 minutes if any one of you even Sai, thank you, Sai. Right. There's a lot of MCQs in this particular paper, right? All right. The others, if you have not gone through the paper, do you want to go through it, or do you want me to discuss each and every question of this paper? However you say, whatever you say, I'm very comfortable with that. All right, let's start. Okay, I'll ask a question. If any one of you knows the answer, please comment that in the chat window, right? What is the frequency of AC in India? All right, 50 hertz. Sharnav, thank you so much, Sharnav. Everyone else, if you know about this, that the frequency of alternating currents, because alternating current keeps on oscillating. It keeps on moving. Thank you, Sanket, right? In India, it's about 50 hertz. In USA, it's about 120 hertz. The more the frequency, the better quality is the electric current. So in the US, it's slightly more better quality. If I'm not wrong, don't catch me on this. I think as far as Gulf is concerned, there's about 60 hertz of 60 hertz ka current hai. All right, the second one. An electron beam enters a magnetic field at right angles to it, as shown. The direction of the force acting on the electron beam is, all right, upwards. Sharnav says upwards. It's me. Sanket also says upwards. Upwards. Everyone is saying upwards. Everyone sure if it is upwards, right? Okay. Now, for people who have answered this, let me ask you this one thing, right? Now, when you're talking about electron beam, Shadna, Sai, and Imad, all right, I'm asking this question directly to you. When you're talking about magnetic field, right, and electron beam, what? So the direction of electron beam, did you take it as the direction of electric current, or did you take the direction of electric current as opposite to it? What did you do? No, as in, sorry, Sanket, you need to elaborate. Anti-clockwise. Oop. Opposite. Acha, opposite. So, Sanket, you took the direction opposite to the electron beam, right? Okay. How about anyone else? Anyone else? Acha, why? Anyone? Acha, do you all know why should we take it opposite? Why did not we choose? Because we know direction of electric current is what? It is, sorry, what is electric current? It is the flow of electrons, right? So यहाँ पे हम लोग ने क्या लिया? Understand the direction of current is conventional current की बात हो रही है. So if at any point of time, for those of you who don't know, let me just explain this. Where's my cursor? Where's my cursor? Opposite to direction of electron. Thank you. Right. So generally, whenever they talk about an electron traveling in this direction, this is the real current का direction. Real current. Right. Real current क्या होता है? It is the flow of electrons. Right. Vishaka sir, because of connection failure, not able to answer. It's all right, Vishaka. It's okay, right? You know the answer. It's perfectly you're right? This is the direction of real current. But we know that whenever we talk about the direction of electric current, we always talk about what direction? We talk about the conventional. Conventional current. Conventional current. What is the conventional direction? The conventional direction is positive to negative. Conventional current का direction is opposite to the direction of real current, right? So यहाँ पे इस question में when they said that this is the direction of the electron beam, right? मतलब current हमें direction क्या लेना है? We are supposed to take this direction. I mean, I know it's not a perfectly straight line, but please, right? So direction of current मिल गया, right? You use left hand rule में तीन है. This is the direction of current. So in this case, I mean, I cannot keep it on the screen, so you cannot see this. But if I have to keep it like this is the direction of electric current, and this is the direction of magnetic field over here. And the thumb points inside. So the direction, the force acting should be inside the paper, towards the paper. If you have understood, this is how you keep it. If I'm not sure if you can see this very clearly. So this is the direction of current opposite to the electron beam. This is the direction of magnetic field. As per my perspective, this is what it is. And this is the direction of the force acting. So in case if you're having a paper in front of you, I do not have a paper right over here. If I were to have a paper, this would be pointing inside the field. I hope that clears everyone. Number is provided. Thank you. Thank you, Sanket, for doing that, right? I hope this question is clear, everyone. You're given magnetic field pattern of a magnet. How will you find out from it where the magnetic field is strongest? I mean, this is a very simple question. Bringing the conductor at the pole. You don't even need the conductor. What is near the poles? It will be the strongest near the poles. Why? Because of the property of the field lines. There's a property about field lines. Wherever they're crowded, the field line is stronger. So that's one property of magnetism. That's what we'll be using here. two magnetic lines of forces do not intersect each other? Give reason. Anyone knows this? This would show two directions, which is not possible. Thank you so much, Rana. Perfect answer. It's one of the most fundamental properties of magnetic lines of forces that two lines of forces could come very close to each other, but they'll never, ever, ever, ever touch each other. They'll always maintain a safe distance. Why? Because if they were to touch, if they were to cross, they'll show two directions at that point, which is not possible. It's an impossible thing that we have. Right? Say the right hand thumb rule. I think we just did it. I'm sure you know this, so we're not going to do this. What is an electromagnet? A super easy question for 2 marks. Oh my god. What is an electromagnet? Amaya, because okay, Amaya, good job, Amaya. You also said the right answer. Acha, you don't know what is an people. You all don't know what is an electromagnet. An electromagnet basically is a conductor which behaves like a magnet whenever electric current flows to it. जब भी current flow होगा, it becomes magnetized. You have to see it, if I'm not wrong, right, Shadnav? Shadnav, I am not able to see. Just hold on. No, Shadnav, you're from Chinchwad. Excellent. Good job. It's me, Sanket. Electric bell में use होता है. ये अच्छा यूज सिर्फ इलेक्ट्रिक बेल में नहीं होता, बहुत सारी जगहों पे होता है. इलेक्ट्रिक बेल में भी यूज होता है, नो डाउट अबाउट इट, संकेत. राइट. What is the function of an earth wire and why is it necessary to earth the metallic bodies of is the concept of an earth wire clear to all of you? If there's even a single one of you who says nahi sir, earth wire nahi jepa, nahi samajh mein aaya, to please let me know. I'll explain what is an earth wire. It is used to conduct leaking wire. All right, to conduct leaking current. Perfect, good job. So everyone knows what an earth wire is. You do not want me to go ahead and explain what is an earth wire, right? Someone is typing. Who's typing? Shadnav. Shadnav, you're typing. Shadnav. It prevents from shock. It prevents from shock. Yes. Direct path to the ground. Excellent, brother. Okay, to prevent electric shock. Samarth, good job. It prevents from shock. All right. So you'll know this. I don't have to go into details about this. What is overloading? Okay, this is a very interesting thing because in India we have this typical problem of overloading. हमें अक्सर होता है overloading का. What is overloading? When you have a single switch, single circuit, and you overload. What do you mean by overloading? For example, let's say one of you goes to the gym, assuming hypothetical example, right? Let's say Sharnav, because you're answering, I'll take your name. Sharnav goes to a gym. Sharnav, I don't know, you have not seen, you have absolutely zero idea as to how much weight you could lift. But assuming, let's say you could lift dumbbells of up to 50 kgs, let's assume. Okay. Now that's your limit. The maximum is up to 50 kgs, right? So you could easily do 5 kgs, 10 kgs, 15 kgs, up to 50 kg. But one fine day, I'm like, okay, 50 kg pakad. Get hold of one more 10 kg, get hold of one more 5 kg, get hold of one more 20 kg. So what we are doing is, within the same object, within the same you, आपका जो capacity से कहीं ज़्यादा load हम उस पे डाल रहे हैं. This in a very simple example of overloading. So in a circuit, what happens in a single socket, it can give a certain output, but in the same socket, if we go on connecting, like एक ही AC का connection है, वहीं से दूसरा भी connect किया है, तीसरा भी connect किया है, चौथा भी connect किया है, बहुत कुछ कर दिया है, उस चीज को हम overloading कहते हैं. Yeah, at times what happens, there are these heavy machineries, for example, the voltage of current that comes to a home, residential usage is about 220 to 240 volt. But when you talk about heavy industries, it could go up to 400 volts or something like that, right? Now, what happens is, understand, if I were to use one of those heavy machineries in my residential complex, it wouldn't work because of overloading phenomena. So that basically is, how can the circuit be prevented from damage due to overloading? You could use something called as MCBs. MCBs are miniature circuit breakers, which are very common in today's days and time, right? So that's one very important thing. And also one very important thing is overloading करने के लिए avoid putting excess load on the circuit itself. I mean that's pretty common sense. What is an AC generator? States its construction and working. That's a pretty lengthy answer. I'm sure you know this. What is a generator? A generator is something which converts mechanical energy to electrical energy, right? AC generator will produce which current? AC current. You know already that there are two types of electric current. I'm sure you know this. I would still like to just broadly specify. All right. Sorry, I'll just like to take this up. Right. So we know that as far as electric current is concerned, there's two types of current, which is DC and AC. Two types of electric. Quickly, can anyone tell me who invented DC current and who invented AC current? Any one of you knows that? Hmm. We use DC, we use AC current for every. I mean, right now we are using alternating current, right? It's a very important and integral part of our lives. All right, I'll wait for 30 seconds for any one of you to answer. If you know this, don't Google. Can you recall the full form of AC generator? AC is alternating current. Sharnav, thank you. AC is Nikola Tesla. Thank you so much. DC would be Thomas Alva Edison. Edison, the guy who invented the bulb, is the guy who invented the DC current. Now, alternating current is a far superior technology than DC, right? Thomas Alva, acha, Samath. Thank you, sir. Samath. DC current has a lot of uh, problems. For example, DC cannot be transported over larger distances, but AC can be transported over larger distances. If you want to produce a DC current, you will need a DC generator, right? If you need to produce an AC current, you will need an AC generator. So in our power plants and everywhere, they use these generators to produce electric current. The basic mechanism, I'll want to combine and explain this in a very easy way, right? Basically, what happens, the phenomena of electromagnetic induction is, what do you mean by motive power? Motive, MOTIVE, or you're talking about electromotive force, EMF? Amay, if you're talking about EMF, that's a different thing. I'm not sure as to what you mean by motive power, right? So generally, so EMI, as we were talking about EMI, what happens is whenever the magnetic field acting on a conductor changes, the moment it changes, it produces or it induces electric current, right? This phenomena is used in generators. For example, what is done is, let us understand a very easy example of a hydroelectric power plant. In case of hydroelectric is used in homes, the current that we are using right now in homes is an AC generator से जो main power supply है वहाँ से AC current आता है. Thank you, Sai. Right? So let's say there's this dam, लाल कलर का dam है. I mean, why not? Right? There's this dam, and we know water. I mean, I'll take blue water if you like. There's water stored in a dam, and this water contains potential energy because this is stored at a great height. This water is made to flow under the influence of gravity, when the potential energy gets converted to kinetic energy. And this water falls on huge turbines. Turbine, I'll just change this colors to you. They're these turbines, right? And the moment this water falls on these turbines, what happens is the turbines start going goal, 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 goal. They start rotating. They start rotating, and these turbines are connected via an axle to a generator. And inside the generator, what happens? There's this magnet. There's this iron core. There are these magnets. Let's say north, south, armature coil. I'm sure you have done this, right? And there's this axle. This axle. Now, what does electromagnetic induction says? That as this conductor rotates inside this magnetic field, it will generate electric current. This is basically called as a generator, right? If it has a split ring, okay, if it has a split, that's a DC generator, because DC, direct current. And if it has full rings, then that's an AC generator. Why does that happen? If you were to look at the graphs of AC and DC, I'll just try to pull this up somewhere. Wait a second. If you were to look at the graphs of AC and DC, DC ka graph would be like, that's time and EMF like this. ठीक है, it breaks because वो split है तो break होता है. और AC का graph जो है, it's a sinusoidal wave, ये ऐसा continuous जाएगा. Like, this is again just FYI, you don't have to know all of this, right? So the diagram, I'm sure you know. If you want, I could show you over here. AC generator would be, just hold on, 78. That's AC and DC. And I'll show you the diagram of an electric motor rather. No, wait, I'll show you generator. I'm just skipping the slide. Yep, this is a basic structure of a AC generator, right? What do we have? We have this iron core, right? We have this armature coil, which is made up of copper. These two green things that you see over here, carbon brushes, carbon as in graphite. Graphite is a good conductor. They're placed between two magnets. Now this magnets will produce a magnetic field, right? Fleming's right hand rule. So there's magnetic field, and over here there would be an axle from which it is connected to this turbine, right? So we also, and because of which this would be rotating. So we know the direction of the force acting, we know the direction of magnetic field, it is north to south. Then we can find the direction of the induced current. This ring R1 and R2 is a complete ring, it is in pura contact with that axle beach wala. Hence it is a AC current, AC generator. If that would have been split, if I have a picture of DC. All right, DC generator, you see this is split. There's a gap between this. There's a gap here. I'll take a better color for you. There's a gap here and here. That's a split ring. That's DC. So whenever, in case of motors or generators both, whenever there's a split ring, it has to be DC. Whenever there's a slip ring, it is a AC generator. AC generator, yeah, AC motor, whatever it is. All right, coming on to the MCQs, people. The relationship between electricity and magnetism was discovered in 1820 by Hans Christian Ørsted. We know this. Which of the following statements are true? Michael Faraday, someone said. Michael Faraday discovered EMI. This relationship between electricity and magnetism was discovered by Hans Christian Ørsted. Right? Michael Faraday discovered EMI, electromagnetic induction. Which of the following statements are true? The magnetic field lines emerge from North Pole and end at South Pole. The magnetic field lines never intersect. The magnetic line is stronger near the poles and at other places. All of the above. Obviously, the answer over here again would be all of the above. Yeah, pretty easy. The direction of the field line due to a straight current carrying conductor is given to us by the right hand thumb rule. I mean, the right. Why is this not working, Baba? All right, it's given to us by the right hand thumb rule. We know this. I'm sure you know this. The magnet whose magnetism lasts only for the duration for which the current flows is called as a electromagnet. I think we did discuss about this. Imad, are you able to hear me now? Imad. Yes. All right, Imad. A stream of positively charged alpha particles moving towards west is deflected towards north by a magnetic field. The direction of the field line is, what do you think? You know, east, west, north, south direction sabko pata hai. That would be what? Into the page, out of the page, south. South का option नहीं है यार कहीं. Shadna, there's no option called a south over here. B. Sorry, out of the page. All right, okay. Let's check this. What I'll do, just give me a moment, please. I'll just quickly also get out the answer key for you, just in case, so that you could download it later on. The answer key, otherwise I'll forget by the end of it because it's about to be over. Into the page. Sai Sharat says into the page, and I'm sorry. We were at question number. Acha, in this case, what is given to us is a positively charged alpha particle. So what do you take the direction of electric current as? Do you take that as the direction of electric current? Yeah, do you take the direction opposite to it? Anyone who could answer me that, that would be wonderful. Right. So the answer over here is B out of the page, as rightly said by Shabnam. Good job, Shabnam. A force acts on a current carrying conductor when placed in a magnetic field. This is the principle of working of force acting on a current carrying conductor when placed. What do you think? Bell, motor, generator. What is it? C. Imad says C. Electric motor. Perfectly fine. Electric motor works on Fleming's left-hand rule, and this is what they are talking about. Which of the following are not the sources of direct current? Bicycle dynamos, dry cells, car batteries, and DC generators. Any idea, anyone, about this? The answer is A. In this case, A. DC current is basically cells and batteries. Okay? So dry cell is a source of direct current. Car batteries is a source of direct current. DC, I mean, the name itself is DC generator, right? Bicycle dynamo. Do you know what a bicycle dynamo is? Any idea, anyone, what a bicycle dynamo is? Not now. It's not a very commonly used thing these days. It's a small little generator that was placed on bicycles in olden times when there were not enough street lights and stuff like that. There was a small little generator called as a dynamo kept, and this was kept near the rear wheel or the front wheel. So as the wheel will rotate, the turbine will rotate, and it will produce electric current, a very small amount of electric current, and that will be connected to the headlight. And the faster you go, the brighter the light would be, because more electric current would be produced. So in this case, that is the answer. That bicycle dynamo is the right answer. This is not a source of direct current. Which wire has green colored insulation? Come on, this one is easy one. B. Earth wire. Excellent. This is the direction of induced current is found using. Come on, very easy. कौन सा है? Ninth question का answer. The direction of induced current is found using A. Right hand thumb rule. कौन बोला? साई नहीं साई. Induced current की बात हो रही है. D. Fleming's left hand. No, it is C. Ayush. Thank you, Ayush. Right answer. It is Fleming's right hand rule which says this is induced current, right? Anyone confused about this? Fleming's left hand rule says normal current, right hand rule says induced current, right? The magnetic field lines around a straight wire carrying current are a concentric circle. Perfect. Right? That solves our paper here. Any questions anyone has about this paper or any other thing as far as this chapter is concerned? I'll love to solve it out right now. No questions. All right, excellent. If you have no, Vishaka sir, will you please show the position of fingers in Fleming's left-hand rule? Vishaka, Fleming's left-hand rule, same thing. 3 fingers. I mean, I cannot. 3 thumb, forefinger, and your central finger. Stretch them mutually perpendicular, right? Now, left-hand rule says what? If the forefinger points in the direction of magnetic field, the central finger points in the direction of electric current, then the thumb points in the direction of the force. This is what it is, Vishaka. Is that clear, Vishaka? What was the answer of the first question, Imad? Frequency of AC in India, 50 hertz. Fuse wire has high resistance or low resistance? Low resistance. Ayush, fuse wire has low melting point, right? Resistance jahan tak kya hai, it has a slightly okayish resistance because it cannot have a very high resistance. If it has a very high resistance, what would happen is current jo hai, it will start blocking the current flowing. Which Fleming's hand rule is applicable to DC generator? Is right hand. Fleming's right hand, hands down. Does the earth wire get affected with rain or earthquakes? No way. I mean, if it is properly grounded and everything weird, it should be okay. There should not be an issue. Vishaka Sihagad. All right, Vishaka. Thank you. All right, I'll end the session over here, people. I hope you have understood this session, and we'll see you all soon. Thank you, everyone. Have a good night. Take care. Bye bye. Thank you. Thank you so much, Sanket.